SwayamPrabha. Digital India. Educated India.
Okay, so welcome back. So let's look at now the property tables. Most of the substances which we are interested in are difficult to provide some kind of empirical relations between pressure, volume and temperature. Now for simple systems such as water, of course, which is quite widely used and it's very complicated system, it's easier for providing the information such that a table can be used with all the properties. Okay, for other cases, for example, you want to look at very high temperature pressure, many times it's difficult to do experiments, you may not be able to obtain the properties, and then you might like to use some kind of empirical relations for doing that, and that's something called equation of state. So the tables of the properties became popular, which was introduced by Richard Mollier, and hence is become quite prevalent in various different engineering applications. So we'll look at it, we'll look at understand the table properties and how to make use of it. The most common example would be water and refrigerant for of course obvious reasons for many system in steam engine and other applications. Okay, so as I said, sometimes the relationship among different properties are too complex to express by simple equations, and this is true for water, and thus is easier that properties should to represent in some kind of table. And then there are other properties which are difficult to measure, such as entropy for example, but it has a relation with other properties which are measurable. So you represent those properties in measurable properties form and then put it in table. Now typical table which are provided in the appendix of the book are for water and refrigerant. Now you will see that you will have the properties temperature, pressure, specific volume, internal energy, and then two more additional properties will be introduced, which is H and S. Okay, H is something which we are going to talk now, but S is your entropy, and this is related to your second law of thermodynamics, and we are going to talk much later. So H is defined as U plus PV, and the reason for that is commonly or frequently encountered in the analysis of control volume. So you have your internal energy and as well as your PV energy, and thus this becomes more useful that for the sake of convenience we put it together, okay, as U plus PV and defined a term called H. And this particular PV we have already discussed in mechanical energy. This is nothing but energy of and that's what different units gives you. For per unit mass, this will be the unit, and for the case of total enthalpy, it will be simple total internal energy plus PV term. Okay, so this is included in your tables for helping you to solve the problems much easier. Otherwise, you have to always calculate the PV term also. So this is something which we are going to make use of it in our calculations. So let's look at it how these tables look like. So we'll start with table A4, which is saturation properties of water under temperature. What does that mean? It means that the first column of the table will be temperature, and for each temperature you will have a saturation pressure values. So for 85 for example degree Celsius for water, you have 57.868 kilopascal as saturation pressure. Okay, and the corresponding saturation liquid and saturated vapor volumes, specific volumes are given in this. Okay, this is a unit meter cube per kg. So this is your specific temperature, this is your corresponding pressure, this is your specific volume of saturated liquid and specific volume of saturated vapor. There are other columns which I have missed out for the sake of just to illustrate only the specific part now. So this is what we are going to use as a nomenclature. VF stands for specific volume for saturated liquid. F mainly is for fluid, so you can say saturated fluid, but let's just state liquid here, and G for gas, but it is for saturated vapor. Okay, and then we are going to make use of this VFG, which is nothing but the difference between Vg minus Vf, because the volume of the gas or saturated vapor will be much larger, and thus you will have Vg minus Vf. Now in addition, you will have another column in this A4, so which will also have this enthalpy of vaporization, okay, HFG, okay, which is nothing but Hg minus HF, okay. So we are going to use that as well, okay. Now this is for saturation properties of water under temperature, and the other case is saturation properties of water under pressure. This is relevant for the case where you have pressure versus volume as your diagram, and you have this phase diagram, and what you have done is you have kept your temperature constant, and so you are decreasing the pressure. So this is T some constant, and this is another temperature T2, right. So for a given temperature, this is your 85 and this is, let us say, 95 degrees Celsius, okay. So if somebody asks a question that, well, this is the condition, what is the saturation pressure? Well, essentially it means that this is your saturation pressure for a specific temperature T1, and this value is nothing but this value is 57.86, and similarly for 95 P is your 84.609 kilopascal, okay. So this is how we are going to learn a bit on it. This is the case for saturated water pressure tables. So the pressure is given, and for given pressure you have saturated temperatures. For example, for 100 kilopascal pressure you have 99.61 degrees Celsius, and for 1 atmosphere, which is this, you have 99.97 degrees Celsius, which we approximate to 100, okay. Then you have this saturated liquid volume, vapor volume, then you have internal energy also, okay, and this is enthalpy. So this is U, this is H, okay. So this is the U of fluid, or this is your evaporation, which is nothing but U G minus UF, and this is your saturated vapor, okay. So and this means that the internal energy of G is going to be much higher than the liquid, which you can also see here. This is much higher than the liquid. And similarly for enthalpy, now it also includes PV term, okay. So this is for convenience, you can also calculate separately, but this is given to you, which means essentially a lot of properties are available for you to make use in the analysis. Okay, so we will try to do some examples. So let us take a case just for the sake of illustration here. So you have saturated liquid and saturated vapor states, and this is the case of temperature, volume is plotted. What you have been asked is, you have a system which is at 90 degrees Celsius, and this is the saturated liquid. Corresponding pressure would be 70.83. If this is being asked, you can find out directly from the table A4. So this is the corresponding pressure. You can also find the Vf and Vg. You can also find VFG also from the tables, okay. This is an example of pressure versus volume, and for 100 kilopascal you can find out what particular condition it is. So this is going to be like this. So what is your temperature for such a system, okay. You can look at A5, because A5 gives you this pressure and the temperature. So for the case of this, in principle, this is your 100 kilopascal, and the corresponding temperature here would be your 99.61 degrees Celsius. Okay, so that would be your T sat here, okay, and this corresponding state would be your saturated liquid, and this would be your saturated vapor, okay. Okay, all right. So let us try to further analyze this. We are going to introduce quality X, and this particular quality X is the ratio of mass of vapor to the mass of the mixtures, okay, which essentially means M is equal to M vapor divided by M total, and this tells you that how much amount of vapor is present in the mixture. So again, you have a P or T as a function of V. So whether if for given conditions your system lies here or system lies here depends on what is the quality of your system. Now so we will try to do some analysis or some exercise here. what we are going to consider is that when you have a saturated system, for example, in the case of system containing Vg volume, specific volume of vapor, and Vg specific volume of liquid can be approximated as the V average of the system. So let us look at some mathematics here. So here the total volume of the system, which contains, let us say, vapor and liquid, can be considered as Vf plus Vg. Okay. Now Vf is the total volume of the fluid, okay, which is nothing but the mass of the fluid or the liquid multiplied by the specific volume of the liquid. So this would be your m of f and v of f plus m of g and v of g, and this is your total volume. Now you can divide this by your mass. So this is going to be m, and this mf by m total, okay, this is total mass, Vf plus mg by m total Vg. Now we have already defined that x is nothing but mg by mt. So this is going to be 1 minus x, because we know that mt is nothing but mf plus mg. Okay. So in that case the ratio this will be 1 minus x Vf plus x Vg, or in other word you can write this as Vf plus x Vfg, okay, where Vfg is Vg minus Vf. Okay. So this is going to be the V average of the system. Okay. Now you can also write other properties. You can also write your internal energy of the system as Uf plus x Ufg. Similarly, you can write H as Hf plus x Hfg. So this is something already summarized here in this particular slide. This is already summarized here. Okay. So x, from here you can find out x as simply the V of the system, specific volume of the system, minus the specific volume of the liquid and Vfg. Okay. So this, in case you are not aware of the values, but if the graph is given, if the PV diagrams are given to you, you can make use of the geometry to find out the quality. For example, this here is an illustration. So A is, of course we know, is a saturated liquid line, so is on top of this line A, and C is on top of the saturated vapor. B is your system, okay, and system's volume is V average, and this distance is nothing but V average minus Vf, which is nothing but this one, okay, and this one, the total difference here from here to here is Vfg, because this is Vg minus Vf. Thus you have geometrically, you have the numerator and as well as the denominator, and thus x can be simply the distance AB divided by AC on this PV diagram. The other thing which we should remember is that the average of any thermodynamic property for the saturated system lies within the saturated region, which essentially means that Y average, which we are generalizing, which is nothing but Yf plus x Yfg, where Y can be V U H. The Y average should be greater than or equal to Yf and less than or equal to Yg, which essentially means that the specific volume of such a system V here should lie somewhere in this region, okay, for any point. So for example, here we are saying specific that this one should be here, but you can have somewhere here, okay. You can have a system where you can keep this specific volume constant as well. So this should lie between these 2 points, okay, for each particular variable which you are keeping constant here within this domain. Okay, so let us take an example and apply this concept. So this is a rigid tank which contains 10 kg of water at 90 degrees Celsius. Okay. If 8 kg of water is in the liquid form and the rest is in the vapor form, determine the pressure in the tank, and the second part is the volume of the tank. Now what is given to you is 90 degrees Celsius. It is also given that 8 kg of water is in the liquid form. So you know your mass of fluid, you know your mass of gas in this vapor liquid system, you know the temperature as well. It is already stated that this is a saturated system because the vapor and liquid masses are given. So we know this is within the saturated region. Okay, so what is the pressure? Pressure would be simply saturation pressure at T equal to 90 degrees Celsius, because the system is saturated because of the vapor liquid are at equilibrium and is given. So this is something which you can clearly use some table, and the table you are going to use is this, which is A4 table. The temperature is given to you 90 degree and the corresponding pressure is this. So this becomes your saturation pressure. So this is the answer for the first question. Okay, so this is your pressure. Now what about the volume of the tank? So you can solve this problem in two ways. So let's first look at what is volume we have to write in this, because we have been given already mass of the fluid and gas. So we can simply write total volume is mf Vf plus mg Vg. Now we know already Vf and Vg from the table. So you can simply plug in all these values. So 8 kg, and then you have this 0.001036 plus 2 kg into 2.3593 meter cube per kg. Okay. Hence your value is 4.73 meter cube. So this is one way of solving such a problem. You can also try in different form where you start with the quality, okay, because one mass is given already, x is equal to 2 by 10, okay, which is 0.2, okay, because this is your mg, okay. So x is given to you. So you can make use of x, and you know that v is nothing but Vf. So I look at it, I am using specific volume here, plus x Vfg, okay, because Vf is given here, Vf is given, okay. So Vf plus x Vg minus Vf. So we plug in these values which from there, and this value would be 0.473 meter cube per kg, okay. Then the volume is nothing but m times specific volume. So we know m total, which is given as 10 kg multiplied by 0.473, and this is going to be the same answer. So there both ways will work. Sometimes one form is much easier than other one. So let's take another example. This is a completely different fluid. It's a refrigerant. So this refrigerant tables are given in A12. So what you have is a 80 liter vessel which contains 4 kg of refrigerant at a pressure 160 kilopascal. Determine the temperature, the quality, the enthalpy of the refrigerant, and the volume occupied by the vapor phase. So you can find the specific volume, which is V by m. So you can convert this thing into meter cube, which will be this. So this will be the volume divided by 4 kg. This becomes a specific volume, right? Now the question is this specific volume within the saturated region, or is it compressed liquid, or is it superheated vapor? That is the first thing which you have to find out. So that means you need to look at the table. Okay, so let's look at this table. This is 0.02, and the corresponding pressure is given here. 160 is somewhere here. So this is your 160. The saturated temperature, which is the first part, is already given. So we can simply use this. And these are the values for saturated liquid and saturated vapor. Now clearly our value of 0.02 is greater than saturated liquid, but less than saturated vapor. Hence it has to be within the saturated liquid region. So this is a saturated vapor liquid system. Okay, so hence your system is somewhere here. So you can find out from the table these values, and then you can calculate the enthalpy of the refrigerant. Enthalpy of the refrigerant would be your H HF plus X HFG. which essentially means you need to find out what is x. Similarly, the second part is something which is a volume occupied by the vapor phase. So, you need to find out the volume of your vapor, which essentially is given to you, but then you need to multiply by mass of your vapor, and then you have to find out. This you can find out from again the quality. So, the first thing is to find out the quality. So, what is the quality? Quality we have already defined, V as Vf earlier, x Vfg, okay, or in other word x is V minus Vf by Vfg, and Vfg is Vg minus Vf. Okay, so you have the values of F and Vg, you can find out quality, it turns out to be 0.157. Okay. Now you can plug this 0.157 here, so, and you know these values of Hf and Hfg from the table. So the H, if you plug in, because you have this Hfg also is given, so let me go back, this Hfg is also given to you. So this Hfg is this and Hf is this. So make use of these two values. So you can replace this here, and then you have the value 31.18 kilojoules per kg plus 0.157 multiplied by 209.96 kilojoules per kg, and this is going to be 64.1 kilojoules per kg. Okay. So once you have this H, so this is the enthalpy of refrigerant. So you can also find out m of g now, which is much easier because you have the value of x and you already know the total mass, which is 4 kg. So this is you can calculate. You can also calculate volume of gas by multiplying mg by Vg. So because already you have got mg information, you have mg, you already know Vg from the table, okay, and this turns out to be 77.6 liter. Okay, so you can do the rest of the analysis of yourself, but this is the procedure of solving such a problem. Okay. So I guess this was interesting that you made use of the tables to solve some process related problems, and we will continue this discussion in the next lecture. Okay, so I shall see you in the next lecture.